Okay, so welcome back. This is part two in our series where we're going to give you a very simple explanation to help you understand control systems. Now, if you've ever looked into technical areas like control systems, guaranteed you're going to see university professors and others who just copy and paste these very complex 25 pages of differential equations and you're supposed to understand it. That's not how I work. In the videos in this channel, we try to give you a conceptual, intuitive understanding of what's going on, so in the end, you can make your own equations. So what we're going to do in this video is we're going to take the next step from the previous introductory video, and I really encourage you to look at that introductory video because we set down some very basic foundations and basic understandings of control systems. And we use as an example what you see right here, you driving a motorcycle. And that turns out to be a really good intuitive example because you may not know it, but you are a really good control system. So it will be a lot easier to understand if you think about what you would do when driving a motorcycle or a car or any other vehicle. So we're going to use that as a basic foundation. We're going to try and simulate you riding a motorcycle and how you control a motorcycle. And ultimately, we're going to develop a piece of software that will give you a nice visual understanding. So for example, here I've got a simulation of a control system, and I slam the throttle and the speed increases over time. And we're going to show, if you're into writing software, we're going to show you how to write a very simple piece of software. But even without writing the software, it will give you a really good understanding of how things work. So in this video, we're going to take the next step from the previous video, and we're going to look at what is arguably the most important part of a control system, and that is the device being controlled, in this case, a motorcycle. So, if you don't know how a motorcycle works, you can't control it, right? You have to understand the details of how a motorcycle works in order to know how you're going to control it. You need to know about the throttle, about the speedometer, and all those things. They seem very simple, but with a general machine that you have to control, you really need to understand it first. Unlike a lot of people who focus on control systems, they just throw you all this control system information. That doesn't help you if you have to control a real-world object and figure out how it works. So we're going to focus in this video on understanding our motorcycle, which is very similar to a lot of machinery in the real world. And we're going to, in future videos, expand on that to simulate other machines and hopefully give you a lot better understanding how the real world works with control systems. So here you've got your machine that you're going to control. Let's take a look at how we would simulate that in some software. So in the previous video, we came up with this very simple model of you and the motorcycle. And it's kind of a logic diagram showing the inputs and outputs and how this thing works. And basically you as the controller are calculating an error between the speed you want to be. We said if you want to be 60 miles an hour and the actual machine miles per hour coming from the speedometer is 0, the error is 60 miles an hour, and you have to do something in your head to understand how to control your motorcycle to make it go 60 miles an hour. And the way you do that is you twist the throttle, but you need to understand that in your brain that you twist the throttle a certain amount, and that will make the motorcycle go faster. So we're going to, in this video, focus on this block, which is the motorcycle. It has a throttle input and a speed output. So how does this work internally? One way to kind of understand a motorcycle and how it responds is to look for real-world data on a real-world motorcycle. You don't see that a lot. You see people looking at conceptual equations and stuff, but nobody looks at real-world stuff. So I went to the internet to look for response data for a real motorcycle. And there's a bunch of websites that have it. This is from a website called motostats.com. Really wonderful website. It's got a lot of information about different motorcycles and how they respond. And what I've got here is just a random graph I took for a Honda CB500F, and it shows the acceleration through the gears. And on the bottom of this graph, I go from 0 to about 35 seconds. And vertically, I'm going from 0 to about 130 miles per hour. This is vehicle speed in miles per hour. So this gives you a really good indication of how this particular motorcycle responds over time to a control signal. And that control signal is a rider sitting on it, twisting the throttle and trying to make it accelerate as fast as possible. And what this says is if I get on the motorcycle, turn it on, and twist the throttle to maximum, over about 35 seconds or so, it will increase speed, it will accelerate with a curve like this. And after about 34, 35 seconds, it will have hit 110 miles an hour for this particular motorcycle. So that's really good information. We can now model this motorcycle and have something to compare our results with to say, hey, can I model my motorcycle in my software and come out with a response over time that looks kind of sort of like this. So really good to look at real world data. So we're going to try and come up with something, some model of our motorcycle that gives you a response that looks something like this. Of course, that's for one particular motorcycle. It's going to change a lot and we'll talk about that. But this is really good to have this input data. The basic model we have so far for our motorcycle is it takes a control signal in, which in our case is a fuel valve position. As we mentioned before, you twist the throttle, that basically opens or closes the fuel valve on the engine of the motorcycle, and the output, the result, is the speed of the motorcycle in miles per hour. So it's a really simple block diagram that's used very often in control systems and other types of analyses where you have an input and you have an output. The input is the position of the fuel valve based on your twisting the throttle. The output is how fast the thing is going, right? Very simple. What we have to do is we have to figure out how to make a model inside this machine block that takes a fuel valve position in and gives you motorcycle speed out so that it looks like this. So what do we know from this? If you look at this, we know that the engine speed is proportional to the fuel valve position. In other words, if my fuel valve is fully open, I've twisted it all the way, but my present speed is 0, the engine's running, I twist the fuel valve, what do we know about the future speed of this motorcycle? Well, if it's running and you twist it to maximum throttle, that thing's going to accelerate like we saw here, right? It's going from 0 miles per hour, it's going to start accelerating. So we can see that there is a relationship between the speed of the motorcycle and the control valve or fuel valve position. It's proportional in some way. We're not sure how, but it's proportional, which means the more wide open the fuel valve is, presumably the faster the motorcycle will be going. So we can kind of predict what the speed will be in the future based on the present fuel valve position and the present speed, right? So if the present fuel valve position is fully open and the present speed is 0, I'm not going anywhere, and I just slam the throttle, we can predict with pretty much certainty that in the future, in the near future, that motorcycle speed is going to have increased from 0. We don't know exactly how much, but we can predict. Very, very important concept to understand. You can predict the future with some sort of certainty. How can we define what that future speed is going to be? Well, we know it's going to be a function of what the present speed is, plus some additional speed, either plus or minus, right? So if the present miles per hour is 0, the future speed is going to rely on this fuel valve position. So if I'm at 0, present speed is 0, and the fuel valve position is at maximum, it doesn't take a rocket scientist to guess that the future MPH is going to be more than what it is now. We don't know exactly how much, but it's going to be the present speed plus some factor to add from it. So this is a really, really important equation. And what we're doing, we're saying is there is some number that we can multiply this fuel valve position by to give us an incremental new speed that we can add to this present speed. All we're doing is we're saying if we're here and we know in this case the guy slammed the throttle to maximum, we can pretty well predict that this future speed is going to look something like this. right? It's either going to be like this or it's going to be like this or whatever, but we know it's going to be increasing. So we can come up with an equation for the future speed of this motorcycle using something like this. The present speed plus this additional factor that depends on the fuel valve position and some number that we don't really know, but it's a constant number depending on the motorcycle, right? So here we can predict the future, and this is really, really important in understanding how we're going to simulate this to predict what the future speed is going to be. This B factor, what is it? Well, it's basically saying if I open the fuel valve by, say, 10% more than it is now, how much faster will the motorcycle go? So it's giving us a number that, for example, if I open the valve a little bit, how much faster will the motorcycle go? We don't know off the top. You got to think about the motorcycle itself and how it will respond. So if you open the fuel valve by 10%, how much faster will the motorcycle go? Well, what does that depend on? Well, if you think about it, there's some things you really don't have any control over. Like if you have a really heavy driver sitting on the motorcycle and you increase the fuel valve by 10%, is the motorcycle going to go faster in the next second than if it was a driver that weighed 10 pounds? Well, no. Usually, if the driver is light, the motorcycle can accelerate a lot easier than if the driver is heavy. But that you really don't have any control over. Also, the grade that the motorcycle is sitting on. If you're trying to go uphill and you increase the valve by 10%, if you're going up a hill, the motorcycle isn't going to go as fast as if you did the same 10%, but you're going downhill. So these are kind of external factors that you don't have control over, but they kind of affect the answer to that and figuring out what that B factor is. The stuff that you do have control over that is dependent on the motorcycle itself is, for example, the engine horsepower. If you've got a very, very, very powerful engine and you increase the fuel valve by 10%, that thing is going to go a lot faster. It's going to accelerate a lot faster than if it has a very small engine horsepower and you do the same 10%, it's not going to accelerate as fast, right? It needs more power to accelerate faster. So this is something that comes into play when we're looking at this B factor. Also, the gear ratio. If you've ever driven a motorcycle or a bicycle with a gear changer, you know that as you change the gear ratio, the acceleration and the speed can change as you change that ratio. So that's another factor you have to consider when looking at your particular motorcycle that you're going to model. Also, mechanical delays and inertia. Again, if it's a really, really heavy motorcycle and you increase the valve by 10%, it's going to be more difficult to accelerate it than if it's a very lightweight motorcycle or a bicycle. It has less inertia and it's going to be easier to accelerate it. Also, mechanical delays. Maybe your motorcycle, when you change the throttle position, it takes 10 minutes to change the position. It's not going to go as fast. So there's some timing issues and some specifics of your motorcycle you need to take into consideration when you are modeling your motorcycle. So that B factor kind of takes all of those into consideration, and hopefully we can come out with one number that encompasses all those values. And to do it, this is kind of the net response of the motorcycle considering all of those things. And if we can get our model to act like this, we've kind of taken into account a lot of those. So this is very helpful to have this final answer. So what we're doing is we're saying if I open the fuel valve by 10%, how much faster will the motorcycle go? We also need to take into account the fact that we need to specify when are we going to measure the next speed. How much faster will the motorcycle go? Well, are you saying how much faster will it go in 10 minutes or in a tenth of a second? So it's really important to specify not only you're increasing the fuel valve by 10%, but you have to say, I want to know the new speed after a tenth of a second or 5 seconds or 10 seconds, because, after this amount of time down here, it's going to have increased to here. But if you're saying it's over here, this amount of time, it's going to have increased a lot faster. So we also have to specify when are we talking about? When are we going to measure? When we're doing our simulation, what we're going to be doing is we're going to try simulate at each step in time what the new motorcycle speed is going to be. So we have to be very conscious that we have to also include that time difference, the new time, to figure out what the new speed is going to be, because speed is a factor of time. So in our equation, it's going to be the present speed plus some factor of the fuel valve position and of the time step. What time in the future are we looking at? So this kind of gives us a really good, simple equation to understand how our motorcycle is going to respond over time based on this input fuel valve position. And if you think about it, this B is going to be a constant number. We don't know what it is, but it's going to be a constant. And also the time step, assuming it's constant throughout our simulation, that's a constant number. So we can kind of put these two, multiply them together to modify this B to get a new constant. So really it's a very simple, the new miles per hour is going to be the present miles per hour plus one constant times the fuel valve position. So hopefully this can be the very first order estimate of our motorcycle speed at each point in time using just, a constant here and looking at the present speed and the fuel valve position at the present time. So, all of the differential equations and all the confusing stuff comes down to a good estimate of present speed being a very simple equation like this. So now we have, for our machine, we can write some code that says, if I want to figure what the new speed is in the future tenth of a second, I take the present speed plus some B times the present fuel valve position times the constant time step, and that will give me an estimate of the future speed. So now we have, based on what we did in the first video, our model of U as a controller. We said the fuel valve position is some factor A times this input error. We now have the machine model, which is present mile per hour plus B times the fuel valve position times the time step. That's what this machine does. And really, this is all we need to simulate this machine and this controller over time. So what we're going to do is we're going to look at putting that together into a piece of software, and we're going to run it through and see if we can get something that looks like this to model this motorcycle speed versus time curve. Now, one thing to keep in mind, again, control systems are generally very fast acting, right? It's basically software or hardware, electronics that work really fast. The machine is generally a very slow device. As we saw, this motorcycle may take 30 seconds or 35 seconds to come up to full speed. This machine is the reason why we have to go through a lot of this time step simulation. So just keep that in mind, that this is the guy that's requiring this more complicated time step simulation. Before we get into the next video, we're going to start writing the code. Let me give you some of the results of the code that we're going to develop using this equation for the engine and the equation we showed for the controller. And I put in a B factor of 15, and I got a result that looks like this over time. So you can see it's very close to matching what the real world test data shows for this motorcycle. So this tells us we're on the right track, and we can, tweak these numbers to get a better understanding for how the real world device operates. And this right here is the machine simulator that we're going to develop. So I'm going to start that, and I'm going to slam the throttle, and you can see here in this blue I've got the throttle control signal, and red is the speed of the motorcycle, and you can see the actual speed is up to 90 miles an hour here, and here's the miles per hour, and you can see 15 seconds, 20 seconds is up 110 miles an hour, and hopefully it will get up near 120 in about 35 seconds. So 25 seconds, and here's 30 seconds, and it's almost 120. So you can see it's matching kind of close to what this actual real world test data. And depending on the motorcycle, we vary the different constants, but at the end of the day, we want to get something like this. So that's it for this one. The next video, we're going to take a look at writing some simple software to simulate this and come up with a simulator like this. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Otherwise, take care. Have a really good day. Thanks.